Hi there, I am Veronique Florec from the University of Western Australia. Welcome to this course on the economics of natural hazards. I have created this video series for anyone in the natural hazards and emergency management sectors that is interested in learning how we apply economic analysis to the management of natural hazards. This project is funded by the Bushfire and Natural Hazards Cooperative Research Centre. Welcome to the 10th video in the series. This is the last video of this series. I hope that all the videos you have watched have helped you better understand how we apply economic analysis to the evaluation of mitigation options for natural hazards, and that you feel more confident about the whole process. In this video, we will look at how to deal with risk and uncertainty. By the end of this video, you should know the difference between risk and uncertainty, how to conduct a sensitivity analysis, how to interpret the results from a sensitivity analysis, and what to do with the information we get from it. First, we need to know the difference between risk and uncertainty. Risk usually refers to situations in which we know reasonably well the potential outcomes of an event and their likelihood of occurrence, and we can estimate reasonably well those probabilities. Uncertainty refers to a situation in which we don't know either the potential outcomes of an event or their likelihood of occurrence, and we can't reasonably or reliably estimate them. Usually, risk can be measured, quantified, and managed, while uncertainty is uncontrollable and cannot be measured and quantified. We can assign a probability to risk, but not to uncertainty. In practice, this distinction between risk and uncertainty is often difficult to draw, because while probabilities can usually be assigned to most events, we rarely have complete certainty about the size of all risks. Even when a risk can be quantified with some level of certainty, there will be uncertainty associated with the measure of risk. But why is this important? Why do we need to know the difference between risk and uncertainty? Because we need to account for both risk and uncertainty when we're making decisions about resource allocation for mitigation options, and we deal with each in a slightly different way. So how do we do that in a benefit-cost analysis? Let's have a look at an example. Let's imagine that as part of our bushfire mitigation program, we are going to put in place regulations to increase fuel management in private land and make sure that landowners reduce fuel loads in their lands. When we estimate the potential losses with and the potential losses without fuel management in private land, we need to make assumptions about the level of adoption or the level of compliance by landowners. Do we think that all landowners are going to comply with the regulations and reduce fuel loads to the intended level? Or do we think that only a proportion of them will comply? There is a risk that landowners will not do what is required of them, and that the full benefits of the regulation will not be realized. We can draw information from levels of compliance in other land management regulations to estimate this risk and its impacts on the results. Let's say that we have estimated the average annual losses without the regulation at 1.5 million and the potential average annual losses after the regulation is implemented at $700,000. The average annual benefits will then be $800,000 if we have all landowners complying. But let's say that we have information that in the area, usually about 60% of landowners comply with other land management regulations. So if we apply this to our regulation option and assume that only 60% of landowners will be compliant, we have to estimate how that will reduce our benefits. It could be linear, meaning that if 60% are compliant, then 60% of the benefits are realized, which will be 800,000 times 0.6 equals 480,000. So we will have average annual benefits of $480,000 instead. But if the relationship between the mitigation and the benefits is not linear, then it is harder to estimate. We could have different types of relationship that could be represented by different curves in a graph. An exponential relationship, where at low levels of compliance, there are very little benefits, but at high levels of compliance, the benefits are close to being completely realized. Or we could have a logistic relationship, where there is a compliance point below which there are almost no benefits realized, and above which the level of benefits realized increases very rapidly. Or it could follow the shape of a logarithmic function, where even at low levels of compliance, most of the benefits will be realized. I mentioned before the linear relationship, where the same level of compliance is applied to the benefits. But we could also have a different linear relationship, where the level of benefits increases very slowly with compliance. Or we could even think of another type of relationship. We will need to determine which relationship between compliance and level of benefits makes more sense for the mitigation option we are evaluating and the data we have. For all the mitigation options, we will look at all the risks, such as the risk of escape for prescribed burn, or the risk of delays in the construction of a dam, or other risks such as worker fatality, etc. But even if we had a reasonably good overview of the risks, there may still be considerable uncertainty about the predicted impacts and their monetary valuation. Or we simply might not be too sure about some of the inputs in our analysis. So how do we deal with that? We use a sensitivity analysis to test the robustness of the results. And what exactly is robustness? It is the resistance of the results to changes in the information we have used as inputs in our analysis. Sensitivity analysis provide information about how changes in the information that we have used to conduct our analysis, that is, changes in the different parameters or changes in assumptions, how these will affect our overall results, the cost and benefits of the different mitigation options and their ranking. It shows us how sensitive the results are to changes in the values of uncertain parameters and to changes in any of the assumptions we have made to conduct our study. Basically, it tells us whether the uncertainty we have about a piece of information matters or not for the results. If the results don't change much when we change an uncertain parameter or change an assumption, then they are said to be robust results. We can be confident that the decision we make and the mitigation option we choose is likely to continue to generate benefits even when circumstances change that create a change in the parameter or in the assumptions in question. Anytime we conduct an economic analysis, we should do a sensitivity analysis to test the robustness of the results. So how do we conduct sensitivity analysis? Common approaches include the worst-case case analysis, the one-at-a-time analysis, or OAT, and the Monte Carlo analysis. In the worst-case analysis, we assign one of two values to all parameters. We decide on a plausible range of values with the best values and the worst value for each parameter and assign either the best or worst value to all parameters in the analysis. For the worst scenario, the most pessimistic scenario, we assign the least favorable value to the parameters. And for the best or the most optimistic scenario, we assign the most favorable value to our parameters. The estimated net benefits we get from the analysis should be thought to be the most representative for the best and the worst case scenarios. If any of the resulting net present values is negative, then we need to investigate further the critical elements of the analysis. For this, we can use one of the other two techniques, the one-at-a-time analysis or the Monte Carlo analysis, which I will explain in a minute. Now let's just go through a very quick example of our worst-case sensitivity analysis. In our flawed example, we didn't go into too much detail about what assets are damaged and by how much, in order to estimate the losses for the counterfactual and for the different mitigation options. Here, I'm not going to go into too much detail either. I am simply going to show you the results of a worst base case sensitivity analysis so that you get the idea of how to conduct one and, importantly, how to interpret the results of the sensitivity analysis. So in our flood example, we only had a look at the potential flood losses that different floods could cause on the different scenarios, with and without mitigation. Let's say that these flood losses are the result of flood inundations in residential and commercial buildings. But there are a lot more residential buildings than commercial buildings in our case study area. As I mentioned in video number 3, the value that we assign to tangible assets that can be directly impacted by a natural hazard usually corresponds to the reconstruction value of the asset, meaning the amount of money it could cost to reinstate the asset to its former undamaged condition. To keep it simple, in our example, floods cause mostly a need for replacement of contents and only cause severe damage to buildings when they are very, very large floods. In our example, I have assigned the following values for the reconstruction cost of residential buildings and commercial buildings. And you will see the values that I have assigned for the best and worst case analysis. For our original analysis, reconstruction cost of commercial buildings is 400,000 and reconstruction cost of houses is 180,000. In our best case, the reconstruction cost will be cheaper, so floods will cause lower losses, while in the worst case, the reconstruction costs are much higher. Of course, to estimate the losses, there is an additional step, which is multiplying this reconstruction cost by the number of houses and commercial buildings damaged by the floods. These numbers increase as the severity of the flood increases, but at this stage we're more interested in the sensitivity analysis, so to keep the video short enough, I won't go into the detail of those calculations. Also, keep in mind that when you're doing a full benefit cost analysis, you will have different reconstruction costs for different types of floods. The more severe the flood or the natural hazard, the higher the reconstruction cost. Here, I'm just keeping it very simple for the sensitivity analysis. So, compared to the original analysis, this is how I have changed the reconstruction values. In the best case, I have reduced the reconstruction cost of residential buildings by 30% and the reconstruction cost of commercial buildings by 50%. And in the worst case, the reconstruction cost of residential buildings will be 40% higher and the reconstruction cost of commercial buildings will double. That is, an increase of 100%. Here I am only changing building values to keep the example as simple as possible. But remember that when you're doing a full worst-based analysis, you change the values of many other parameters as well, not just the values of the assets at risk. Another important thing to remember is that when we're changing the value of any parameter, we're changing the results of the mitigation options, but also the results of the counterfactual. So if the reconstruction costs of buildings are higher, losses will be higher for all scenarios, the counterfactual and the mitigation options. Now let's see what this does to our net present values. Since the best case analysis reduces the reconstruction cost of buildings, losses are much lower for the counterfactual and the mitigation options. So the net present value are also lower, and vice versa for the worst case analysis. But what we really want to look at here is the proportional change in the reconstruction values of the buildings compared to the proportional change in the results. Notice how the proportional change in net present values for the best case analysis is relatively similar to the proportional change in reconstruction values, whereas the difference in proportional changes for the worst case analysis is quite substantial. This is indicating to us that the results are sensitive when the values for residential and commercial buildings are higher. So if building values are higher, we need to get accurate information on the values and the amount of damage that floods of different sizes can cause. The next sensitivity analysis method is the one-at-a-time analysis, or OAT analysis. In this analysis, we change one parameter value at a time while holding all the other parameter values constant. And we observe how the results change with changes in each parameter, one at a time. This approach can be used to see what happens to the results when we change the most important or the most uncertain parameters. But we can also use it as a sensitivity analysis on all parameters. Usually, we decide on a percentage change to apply to all parameters in either direction: increase in the selected percentage or decrease in the selected percentage. If the proportional change in the results is lower than the proportional change in a parameter, the results are considered non-sensitive to that parameter. But if the proportional change in the results is higher than the proportional change in the parameter, the results are then considered sensitive to the parameter. If we find that varying a parameter has a substantial effect on the results of a benefit-cost analysis, then uncertainty about its value becomes important, and we need to get more information about that parameter in order to increase the confidence we have in our decisions. If the results don't change much despite changes to all parameters, the results are then considered to be robust. The one-at-a-time sensitivity analysis makes it clear for decision makers how the results are affected by uncertainty about the value of a particular parameter and for which parameters it would be better to collect additional information in order to increase our confidence in our decisions. To look at this method for our example, I have increased and decreased by 50% the values of buildings, one at a time, as you can see in this table. The choice of 50% is quite arbitrary. You can choose another percentage change that makes sense for your analysis. The results we get for our net present value from these changes are: in this table, we can see that when we increase or decrease the value of residential buildings, the proportional change in the net present value is much more marked than when we increase or decrease the value of commercial buildings. That's because we have more residential buildings than commercial buildings in our case study area. Our results are quite sensitive to changes in the value of residential buildings. Notice that the net present value becomes negative when I reduce the reconstruction value of residential buildings by 50%. This means that we need to really get accurate information on the value of residential buildings and the amount of damage that floods of different sizes can cause to them in order to make decisions for flood mitigation in our example and to have more confidence in those decisions. And finally, in the Monte Carlo sensitivity analysis, we draw parameter values from a probability distribution. We calculate the results many times, each time using a different set of random values for our parameters drawn from the probability distributions. We can then create a distribution of the net benefits. This method is a more statistically robust approach to sensitivity analysis, but we still need to be careful about the assumptions we make in our analysis, and they should be reasonable and justifiable, and about the probability distributions that we select for the different parameter values. Common probability distributions used for the parameter values include the normal distribution, also known as the bell curve, where the values in the middle near the mean are most likely to occur. Here on the x-axis, we have the values that our parameter could have, and on the y-axis, the likelihood of occurrence for each value. In this particular probability distribution, the point where the curve is the highest, corresponds to the mean or the average. The log normal distribution has this shape, with a high point closer to the y-axis and a long tail, so it is not symmetrical like the previous distribution. It is used to represent values that don't go below 0 but can be very high. We can also have a uniform distribution in which all values have an equal chance of occurring, and we simply need to define the minimum and the maximum value possible. Or we can have a triangular distribution where we define the minimum, the most likely, and the maximum values. And values around the most likely value are more likely to occur. And then there are many other probability distributions. So it is important to have a good think about which one is the most appropriate for each parameter. For this analysis, I will refer you to resources that you can explore to get more details on how to conduct a Monte Carlo sensitivity analysis. Otherwise, I would have to make this video much longer in order to explain the whole process. And you need to have a good understanding of probability distributions to be able to apply this method. Before we finish, I just want to look at one last question. What do we do if we have low confidence in our results, let's say that they are not very robust, and we can't get better data on the key parameters to which the results are sensitive? Sometimes we still need to make a decision, even if we can get better information. The best we can do is make a decision with whatever information is available at the time of the analysis, and make sure that we create models that can be updated as new information becomes available. We know that the future is always evolving. Population continues to increase, risk patterns may change, we may have many changes due to climate change, land use changes can also change risk levels and how risk spreads across the landscape. So in sum, tomorrow's risk is created today. And so our evaluation models need to keep evolving to stay relevant and make sure that the decisions we make take into account the risk of today and how this risk will evolve over time. So it is important that we don't see the results of an economic analysis as final, but as a piece of information that continues to evolve as many factors in our world also evolve. Okay, that is it for this video and this series on the economics of natural hazards. I'm sure you still have a lot of questions, but the idea here was to expose you to key economic principles and help you appreciate the importance of and the challenges associated with conducting economic analysis of natural hazard mitigation. I hope you now feel more confident about reading and interpreting the results of an economic analysis, and more importantly, that you are in a better position to question them and generate interesting discussions. Thank you very much for your attention.